Hello everyone. My name is Man Shi. I come from Beijing Institute of Technology in China. I'm so honored to be here with you to communicate academic questions and ideas. Today, my presentation is about design and experimental test of a model predictive path following control with adaptive preview for autonomous buses. Next, I will introduce the paper following the four parts. Part 1, Introduction. Currently, due to relatively fixed driving paths, captures sensors layout, more policy support from government, much attention has been focused on the development of the lateral control for autonomous buses. With the development of the intelligence methods, various optimization methods such as PID control, slide mode control, fuzzy control, model predictive control has been developed due to its ability to consider the complex constraints and handle a multi-object problem in nonlinear system. MPC is widely used in the path following control of autonomous buses. Various methods have been proposed to describe the relationship between preview distance with speed, such as linear description, fuzzy ruler PSO. However, despite the good performances of PSO, its huge online computational burden has limited the practical application in the path following control. Next, thus a novel support vector machine integrated with the parameter optimized by PSO method is proposed to improve the computational speed in real vehicle application. Overall framework is shown in this figure. The integrated path following control framework consists of three paths: an active safety controller, an adaptive preview controller, an MPC-based path following controller, and PI controller. Part 2 methods, the active safety control. The speed limitation is set as follows. Figure 1a shows the up speed bound when the road friction is 0.6. B represent the upper speed bound when the front steering angle is 20 degrees. In this section, an adaptive preview method which combined with PSO and SVM is applied to satisfy the real-time performances for bus path following control. In general, the proposed methods consist of two stages: PSO online optimize the preview time, SVM offline trains sample data. In this stage, PSO is adapted to optimize the preview time and realize the adaptive response of the preview time to road curvature and vehicle speed, making the tracking error to 0 to complete the path following. The formulation of preview time problem can be expressed as follows. Different combination of C1 and C2 will affect in the performance of the PSO, verified by a large number of experimental results. C1 equal to C2 equal to 0.5 is the best choice for its fast convergence rate. The training and the testing process can be conducted in the following steps: training iteration, testing iteration, and performance benchmarking. Based on the assumption of a small angle and the linear tail model, the vehicle dynamic nonlinear model can be expressed as follows. The side slip angle yaw rate and steering behavior are constant to ensure that the vehicle can steer stably. Aiming at the influence of changing parameter and other measurable disturbance on the tracking performances. The idea of steering angle compensation is proposed. The designed controller can be expressed as follows. Result and discussion. In this section, line keeping on straight curved road maneuver as shown in figure 3 is presented to verify the effectiveness and feasibilities of the proposed layered path following control framework and control method. Figure 4 shows the speed in different cases. We can see that the latter three methods have activated the active safety controller. The steering angle are presented in figure 5. As shown in figure 5, we can see that the vehicle verified off the road in case 1. The maneuver couldn't be finished without active safety control, and it is found that the case 2 and case 3 with a higher steering frequency. As shown in figure 5, we can see that the steering angle and the yaw rate are both in reasonable regions with active safety controller. Figure 6 to 7 present the tracking lateral offset and heading error in 4 cases. It is obvious that the lateral offset in proposed method is far less than other methods. As illustrated, control methods 4 is better than others. With the proposed adaptive preview method, system could further improve the control performances. Compared with case 1, case 4 has better tracking accuracy, smoother steering angle, and safer driving. In conclusion, integrated control system framework is imposed that forces the vehicle to track a predefined path. The active safety controller, the adaptive preview regulator, as well as the predictive tracker are integrated as a whole system under this framework with highly effective performances. A novel PSOLS SVM method is developed to mitigate the huge computation burden of the online controller, hence benefiting in real-time control capability. Also, active safety controller is designed to limit the speed for preventing the vehicle from side slip and rollover. That's all.
Okay, thank you, Shihan, for your